And now finally, paying our debts, we go back to the first half of the first week of this module when we said sequences that are doubly indexed by natural numbers, m and n in this case, if they are sequences of non-negative numbers, then we can switch the order of the sum. We have already used this theorem in a few exercises and in a few proofs during the module, that we could switch the variables in the sum as long as the function being summed here is a non-negative, or the sequences are non-negative. And let's see now that this is actually just a consequence of Tonelli's theorem. How can we frame this as an integral so that we can use Tonelli's theorem? Well, we consider on natural numbers as our space, our sample space. Well, since it's countable, the sigma algebra will be very simple. The sigma algebra will be all the subsets of n. And we have to put some measure on this space. What measure will it be? It will be the counting measure. Because then, with respect to the counting measure, the integral on this sample space of a certain function f with respect to the counting measure, this is nothing but the sum, or if f a non-negative function from natural numbers to set of non-negative numbers. So for any f, integrated with respect to the counting measure is the same as adding the values. And there's nothing particular of the natural number set that we are using here besides the fact that it's countable. So we could replace natural numbers by any countable set. Okay. Let's move on, because this is exactly what we're going to say here in the proof. Take mu to be the counting measure on this space, natural numbers and the sigma algebra being all the subsets of natural numbers. So this measure mu, it is sigma finite. It's important to remark it. This entire theory of product measures and Fubini and Tonelli theorems, they are for sigma finite measures. Why is it sigma finite? Because, well, the natural numbers is the union of points, and each point has finite measure. Each point has measure 1 with respect to the counting measure. Okay. And now we can, this doubly indexed sequence, we can think of this doubly indexed sequence as a function that assigns non-negative numbers to pairs of natural numbers, or that assigns non-negative numbers to elements of the Cartesian product of natural numbers with itself. And because the sigma algebra, and let's ignore the proof of this, it's something that is more a quick exercise if you want, that the product sigma algebra of the set of all subsets of the natural numbers, because the natural numbers are countable, because of that, it will be the set of all subsets of pairs of natural numbers. And, well, this is the largest possible sigma algebra we can have on some space, the set of all subsets. Then, of course, any function with respect to that sigma algebra will be measurable. So this is we're just trying to translate what sequences means in terms of measure theory. So a doubly indexed sequence, we can think of it as just a measurable function from the set of natural numbers product with itself to set of non-negative numbers. And now this, because mu is the counting measure, and if we go back to the previous slide, you will remember I said this identity holds for any countable space. There's nothing special about the natural numbers here when we integrate with respect to the counting measure. So this is all we are saying here in this first equation, is integrate on a countable set a function with respect to a counting measure. And well, the product of a counting measure with itself is the counting measure on the product space, because it will assign to this set K and J, the measure of that set will be 1. So it means the measure of any pair of numbers is 1. So this is the counting measure. And we know when we integrate a function with respect to the counting measure is the same as summing those terms indexed by that set with respect to the summing it over the Cartesian product of these spaces. So this is just translating sequences in the language of functions. We're not using any theorem, any special property here. And now we are using, to go from here to here, Tonelli theorem. The integrate on the product space with respect to the product measure is the same as integrate on one space first and then integrate on the other. But what does it mean to integrate a function with respect to the counting measure? We have discussed this just in the previous slide. This is the same as summing over that variable. M is frozen. So here M is frozen, and this is understood as a function of n only, and we integrate that function, which means we sum the sequence over n. And since these are non-negative numbers, I can write the sum, instead of writing sum over n belongs to n x m n. Since these are non-negative numbers, I can write this as, in this previous language, the sum going from 1 to infinity. And the difference between this notation and this notation is that here we are implying some order in which you compute the sum. But the order does not really matter when all these terms are non-negative. Okay, so here we are summing this, x, m, n. And this is just using Tonelli theorem, that this equals this. And now why is this equal this? Well, that's what I said. The integrate with respect to the counting measure is the same as only summing over n. And when we integrate again with respect to the counting measure, this is the same as summing over m. Okay, so both equalities, this one and this one, and for that matter also this one, these are just translating the sums of sequences in terms of integrating functions with respect to counting measures. And why do we do that? Well, we want to apply Tonelli theorem. Tonelli theorem has been stated for functions on measure spaces. So to claim that this equals this, we use Tonelli theorem. And also to claim that this equals this, so let's write this equal again here. This is again Tonelli theorem. So that means these sums here, they give the same value. So this concludes the proof of the theorem, which says these sums give the same value.